Welcome back. This is the second part of issues related to thermal management in batteries. In this brief lecture, we will address the issue of thermal runaway. What exactly do we mean by thermal runaway? We mean that when there is, let's say, a small increase in temperature, this small increase in temperature gives rise to further increase in temperature, and the temperature raises uncontrollably. This observation is called thermal runaway. This is a significant safety hazard with respect to batteries. So there is a general way of thinking about when thermal runaway would occur. This has to do with feedback. If the natural feedback in the system, in the battery, is negative, then there won't be thermal runaway. But if the feedback is positive, then there'll be thermal runaway. So let us look at this in some context. Supposing you are charging a battery. In some local area, more charge is passed, let's say, due to some reason. Okay, we are not going into the details of the reason why more charge is passed, but assuming some greater charge is passed in some local region, this would lead to increased local voltages. This can also be understood from a previous lecture, for example, where we talked about charging of batteries. In that lecture, we clarified the meaning of this plot, that in the constant current mode, how the potential increases. Please look at that lecture in case you are not sure of why a greater charge passage would lead to greater local voltages. Overall, the consequence of local voltage increasing is the driving force for current to decrease. So when this occurs, there's a local voltage increase leading to lesser driving force, which further leads to lesser current. So this is a form of negative feedback. There is a local increase in charges leading to lesser current because of this factor. In contrast to this, you may have positive feedback. Supposing instead of this occurring, the extra current that has been passed or extra charge that has been passed goes into a side reaction, let's say a gas evolution. This gas evolution, this kind of passage of current may lead to greater temperature. Okay, so more current leading to gas evolution, leading to greater temperature. Then this greater temperature leads to greater current. This is positive feedback. Greater current leads to greater temperature leads to even further current, and so on. This is what leads to thermal runaway. Okay, so this is a positive feedback as opposed to what we had here. Okay, so a random increase in current, there is something in the system which suppresses further increase in current, as opposed to leading to negative feedback, as opposed to negative feedback in a system behavior that shows positive feedback. A small increase in current leads to further increase in current, leading to thermal runaway. This is a big safety hazard, and this kind of behavior has to be suppressed. So in chemical engineering systems, if we want to have an inherently safe design, we ensure negative feedback behavior. So such a negative feedback behavior is also useful in the context of battery. So we are not going to elaborate these issues any further, but you have to be just familiar with this issue of thermal runaway and how a positive feedback in the system may lead to thermal runaway. In the next lecture, we will look at some aspects of mechanical consideration that is relevant to batteries. These mechanical considerations are becoming increasingly important due to the cutting edge research on solid state batteries. We will take up an elementary outlook on mechanical consideration in a subsequent lecture. Thank you.